second lecture given by Adam about effective field theory. So today he will tell us about CP violation in effective field theory, I guess. Adam, whenever you're ready, you may start. Thanks.
Thank you. So I was last Tuesday. I was telling you about more generally about EFT, about the philosophy of building EFTs, and about the landscape of the EFTs we are using in everyday life, yeah, in our work. And today I'm going to focus on a more specific topic, which is CP violation in EFT. How this effects of CP violation, how they are encoded in the structure of the EFT Lagrangians, and how do they affect phenomenology. So this is the lecture. So let me start just like everyone, yeah, with a short reminder. Yeah, what is CP violation? So these particles are these little tennis balls, yeah, and they have spin, and there is this. We have the operation that are the discrete parity, which changes the coordinates and momenta to minus itself. So it will change the momentum of the particle, which will not touch its spin, and it will not change its properties like charge. But because it changed the momentum, the helicity, which is the projection of a spin on the momentum, we also changed from right to left. So parity, as like the mirror, it changes left to right. Charge conjugation is something that doesn't touch the coordinates or momenta, so the momenta stay the same, but it changes the particle into its antiparticle. Yeah, so for example, the particle with charge minus, will change to the particle with charge plus. And then CP is the combination of the two. So, for example, right-handed particle, will change into a left-handed antiparticle. So that's how the CP is realized on asymptotic states, that we are scattering. So maybe one thing that to clarify. Because sometimes there's some confusion about it. Yeah, so CP relates this scattering amplitude. So if we have a scattering of A into B, and the amplitude, for the scattering of the CP conjugate of A and CP into CP conjugate of B, the CP relates this amplitude so that they have to be equal eventually up to some phase factor. On the other hand, CPT, which is the symmetry of every relativistic unitary QFT, relates the processes A to B with the processes B bar, or the CP of B to CP of A. So they are of course not the same. There is one important consequence of CPT, because if A and B are equal, so we have this forward scattering, and then CPT relates A to A, with A bar to A bar. So for example, the 2-point amplitude, or the 2-point function of the particle has to be the same as the antiparticle. And if from this it follows, that particle and antiparticle have to have the same mass, and also they also have to have the same width, the total width. So this is the width that enters. So in particular, the imaginary part of this forward amplitude have to be the same by CPT. So it means that the imaginary part is the width. So the width has to be, the total width has to be the same. So the width of a particle is the sum of its all partial widths. So this equality of the width will tell you that the sum over all decay channels of a particle A has to be this. Sorry, I forgot the A bar here. But the sum of all particle channels. Just haven't make it notes so that I correct it later. So that the sum of all decay channels of a particle A has to be the same as the sum over all decay channels of the particle A bar. And so if you sum it, this is the total width, and this has to be the same. However, that doesn't mean that the particular decay channels have to be the same. So the partial width can differ, but between the particle and antiparticle, here again I forgot a bar, but the total width, the sum over them, they have to be the same. So the consequence is that if you cannot change only one decay channel, if you violate CP, you always have to. If you change in one decay channel, then there has to be some compensation, in another decay channel, because again the total widths of the particle and antiparticle have to sum up to the same. So after this short reminder, of what CP and CPT is, let me go back to this this picture of the ladder of EFTs, and we will be most of this lecture will be sitting here in this in the effective field theory that we call SMEF, that describes the physics at the energy scales of the order of hundreds, also between 100 GeV and 1 TeV, and up to some cutoff that we don't know. This EFT, again, let me remind you, has this sort of an expansion, that we're starting with the standard model Lagrangian, and then we are adding a series of higher dimensional operators, dimension 5, dimension 6, dimension 7, dimension 8, in some consistent expansion over some high scale. And then, as I was explaining last time, we actually want, for reasons that are have nothing to do with physics, but more with our comfort, that this there is actually two expansion scales in this Lagrangian, one governing the odd dimension operators that violate lepton number, and the other governing the even dimension operators that don't have to violate the lepton number. So the question of the day is, so what are the sources of CP violation in the SMEF Lagrangian? And I will try to give a overview. Of course, it will be not complementary or comprehensive, so it will not be a comprehensive overview of this topic, because that would take 10 lectures of 1.5 hours each. So I will put a spotlight on a very few aspects of CP violation in the Lagrangian. I hope it will be give you some flavor of what's going on. Now let me go back a little bit to more technical subject. So how do we see CP violation at the level of the Lagrangian? So we were discussing how the CP symmetry acts on particles, but when we have a Lagrangian, it's built of fields, and we have to understand how we see that if an interaction is CP even or CP odd. So that's the easiest to explain on a scalar field. So for the scalar field, this is the phi here is a scalar field. It describes a spin zero particle. And then if you write it in terms of the creation and annihilation and creation operators, a complex scalar field will have this kind of expansion, where A is an operator that annihilates particle, and B dagger is an operator that creates antiparticle. So if you take a conjugate of that, so the dagger means complex conjugate is the same. Sometimes I use star, sometimes I use dagger, sometimes I use bar in this for describing the operation of complex conjugation. Then this turns into B dagger turns into B, and A turns into A dagger. Then there is also a conjugate on this A. And you see that the operation of taking the complex conjugate giving me the same, except for now the operators corresponding to particles and to antiparticles are interchanged. So this is exactly what we understand by operation of the C symmetry. So the C symmetry acts interchanges in the Lagrangian phi and phi dagger. So this is how C works. Now for P, this is that depends on how we assign the parity to the scalar. So for example, if this is a parity even scalar, then parity doesn't do anything to a scalar. And then CP symmetry again is operation of interchanging phi and phi dagger. So that at the level of scalar fields, the CP symmetry has a very simple realization, and it's very easy to spot if your Lagrangian is CP symmetric, if it's made of scalar. If you change a phi into phi dagger, if and vice versa, if anything changes in this Lagrangian, then it means that it's not CP symmetric. So for the fermions, the discussion is a little bit more complicated, and actually part of the complication is due to the fact that we are actually using very inconvenient variables in most of this discussion. So people like to use so-called Dirac fermions to describe the fermionic particles. And this is convenient if you deal with PNC conserving theories like QED and QCD, but it becomes a little very awkward when you, for example, deal with Majorana fermions, or if you actually discussing this discrete symmetries like C and P. So for this discussion, it's much easier to actually look inside the Dirac fermion and what it is fundamentally made of. So a Dirac fermion is a 4-component, so it is made of two-component fermions. And these two-component fermions here are denoted by psi and psi c bar. And these are actually the fundamental building blocks, in the sense that they actually transform into itself by the action of the Lorentz symmetry. So this Lorentz symmetry is actually the algebra of Lorentz symmetry is equivalent to SU2 cross SU2, and each SU2 acts on its own two-component effect. So it's very easy to see how it's much more convenient to all work actually with these two-component fermions instead of the 4-component fermions to see the action of CP symmetry. So first, the upper component, this psi, describes the spin 1 particle with negative helicity, and the lower component, psi bar c, describes a spin 1/2 particle with positive helicity. So left-handed particle up, right-handed particle is down. So parity exchanges left and right. So parity exchanges these two. So parity acts as phi going into phi bar c. So it turns this Dirac fermion upside down. What about C? So let us look again how this into creation and manipulation operator, because it's the easiest way to spot how C works. And so for the Dirac fermion, this is the expansion into creation and manipulation operators. So we have a particle with spin, so we sum over two helicities, and then we have a annihilation operator for a particle and creation operator for the antiparticle. And now we have the 4-component wave functions that enter into this Dirac fermions. And again, these 4-component wave functions, they are made of two-component wave functions that I call here X and Y. And one thing that when you work with Dirac spinors that is not clear, actually this U and V are very much related. They are sort of reflection of each other. So they are made of the same two-component fermions. So if we write, instead of working with the Dirac fermions, we write separately the upper and we write the two components separately, then actually the C symmetry is clearly seen. So if we write the expansion of phi, it will be given in this form. If we write the expansion of psi c, then it will be given in this form, where the only difference between the psi and psi c is that the operators corresponding to particles are interchanged with operators corresponding to antiparticles. So the action of the C symmetry on spinors is interchanging psi and psi c. So that is, if you're trying to write the same with Dirac fermions, you have to use some C matrices and so on, and it's very obscure. But this is really what it is. You exchange this spinor with the conjugate of this spinor and vice versa. So now it's clear what is CP. So we just put them together. So psi and psi bar c, P interchanges psi and psi bar c, C interchanges psi and psi c. So now if you put this together, CP interchanges psi and psi bar and psi psi with psi psi bar. So again, if you go to this fundamental component, CP operation looks like a action. Yeah, so it's just a complex conjugation, but it's a complex conjugation on 2 component spinors instead of, and not on this 4 component spinors. Yeah, so that's maybe a little bit, that's why it's maybe confusing, yeah, if using Dirac spinors, yeah, but with 2 component spinors, everything is clear. So for example, let me give you the example of Yukawa interactions. Yukawa interactions written in 2 component spinors is this. This is the Yukawa coupling. This is, for example, a scalar. Let's take it as a real scalar like Higgs boson. And this is psi psi c and psi bar c. And this is the same as in Dirac notation. You write a combination of a scalar contraction without gamma 5 and with gamma 5. Yeah, this is the same thing in the 2 component notation. And now, if we apply this operation and we replace psi and psi bar, so what happens is that everything that didn't have a bar now has a bar, and that what had a bar now doesn't have a bar. And you see that these 2, the Lagrangian and the action of a CP on the Lagrangian, are the same, only if the coupling, the Yukawa coupling, is real. Yeah, if it's real, then the 2 things are the same. If it's complex, then it's different. Yeah, the action of the CP leads to something different. So this shows that the action of a CP on a Lagrangian, yeah, is somehow associated with the existence of a complex coupling constants in the Lagrangian. Yeah, at least in this simple case of Yukawa interaction. Let me go to one more example, yeah, which is also relevant to us. What about spin-1 vectors? Yeah, for the spin-1 vectors, situation is a little bit different. Actually, CP is not related to complex couplings, at least not in the usual Lagrangian formulation. So, what is the action of parity on a spin-1 vector? So this is obvious. So the vector potential for the photon, yeah, is a vector. So parity changes, yeah, the vector part, yeah, of the four vector describing the Lorentz potential of electromagnetic field into minus itself, and then it doesn't change the A0 part. On the other hand, C just changes this vector potential, the full 4 component vector, into minus itself. And this, why is that? Because A0 is, for example, associated with an electric potential. Yeah? So if you change particles into antiparticles, yeah, you flip the sign of the electric potential. And so now if you put CP, then these actions together, then CP changes A0 into minus A0, and it doesn't touch the spatial components. Yeah, maybe I wasn't clear that here by I denote the spatial component. So this is X, Y, Z, and so A mu has 0th component corresponding to time, and 3 spatial components, you know, that are denoted as AI. So now we can look what happens with the field strength. Yeah, so field strengths that we use to build the Lagrangian, yeah, is for example, if you have F0i, that is derivative with respect to time of AI minus derivative with respect to space of A0, and here A0 changes, for example, into minus itself, but under parity also, so derivative changes into minus itself, so nothing happens. So F0i doesn't change under CP, and this you know that F0i is related to the electric field. Yeah, electric field doesn't change under CP, and on the other hand, Fij, yeah, is yes. Here I have a little bit. This should be I instead of J, but because you have a spatial derivative, it will flip the sign, and the AI doesn't change, then it goes to minus itself. So now we can build given what we know, we can build a CP odd combination made from this field strengths. So if we build the following combination, F mu nu twiddle F mu nu, where twiddle is defined as epsilon mu nu alpha beta F alpha beta. So this is so the action of this of the Levi-Civita tensor on F. If you write it like that, you can actually simplify it, because Levi-Civita is non-zero only if all of them are different. So this, for example, if it's 0, 1, 2, 3, or 0, 1, 3, 2, and so on. So we can rewrite it, yeah, with just the usual epsilon tensor, antisymmetric epsilon tensor, epsilon hij, and like this. And then you see that this object is made of one f0i and one fjk. So this one is CP even, this one is CP odd. So the whole product is CP odd. So this combination FF twiddle turns into minus FF twiddle under CP. So for example, interactions like this, yeah, that were the Higgs boson couples to F mu nu twiddle, this is a CP odd interaction. Yeah. Another example, yeah, of the CP odd interaction, yeah, is when so-called Weinberg operator, one of many Weinberg operators, many things are called Weinberg operators in the in quantum field theory, but yeah, this is also called Weinberg operator. And this, if you take 3 gluon fields, but you put a twiddle on one of them, then again it will be a CP odd operator. So for spin 1 fields, actually the CP oddness is not associated in the usual language that we use. Is not associated with phases in the Lagrangian, but is associated with the appearance of these twiddles. Yeah, so every twiddle on the field strength will mean that your this transforms into something that is CP that is minus itself under the CP symmetry. Okay, so given that, yeah, we could go and inspect our Smith Lagrangian, yeah, so we know how to spot CP violating interactions, and so our Lagrangian starts at dimension equals 4, yeah. So again, we have this expansion of the Smith, yeah, that goes from dimension 4 to arbitrary high dimensions, yeah, and we'll be inspecting each of this term to spot CP odd operators. Okay, so what is CP odd in this dimension equals for Lagrangian? Yeah, so these guys, the first guys are CP even, yeah, because you have 2 field strengths, so whatever is whatever you transform, yeah, the squared will be CP even. But then you have this so-called theta term, yeah, which is a G mu nu twiddle. And because, as I say, if you see a twiddle, twiddle is CP odd. So all in all, this term is odd under CP symmetry. Now the kinetic terms of the fermions and all the gauge interactions are CP even. On the other hand, Yukawa interactions can be CP odd. So that this was what I was discussing just a few slides ago. That if this Yukawa couplings are complex, yeah, then this terms can be CP odd. So in principle, yeah, there can be many different phases in the standard model Lagrangian, yeah. So there is a priori, yeah, there is many sources of CP violations in the Yukawa couplings. But we know, of course, that this is not precise. This is not the case, yeah, because most of these phases we can get rid of them by field redefinition. So if we only have a D equals 4 Lagrangian, there is only one combination of phases in the YU and YD that survives, and that gives you the physical effect, and that is, of course, the CKM phase. So I will not be talking about this any further, yeah, but so this is some, I guess, this material that everybody knows. But the bottom line is that if we stop at D equals 4, we have only 2 sources of CP violation.
Adam?
Yes, please.
Yes, there is a question by Philippe on the chat. I think it's interesting.
I don't see the chat, so whenever
Okay.
there's a question on chat, please.
So
stop.
why is there no W trigger term for the D = 4 and same for F?
Yeah. So you could write them. You can prove them. You can prove that they are not physical, so they don't give you any physical effects. Or in other words, yeah. So maybe you know the story, yeah, that this theta term, yeah, is not exactly what is the physical parameter. What is actually the physical parameter is a combination of a theta and some combination of the phases in the core mass matrix. So you can prove that because you can prove that if you write the theta term for the W mu, you can always get rid of that by rephasing the leptonic fields. And so this term cannot be physical because by certain U1A transformations, you can remove these terms from the Lagrangian. And the same goes for the U1. So this is a good question. It's not. It's in principle, yeah. This term could for the SU2 could also be relevant, but the structure of the standard model Lagrangian makes it irrelevant because you can always redefine it away. It's not an obvious thing. Yeah, there is a little bit of calculation you have to do, but yeah, that's the fact. Okay, so going back here, so we have this phase in the CKM matrix, yeah. So which is showed itself in many experiments. It showed itself in the K-on, D-meson, B-meson systems, and so this has been observed. And the interesting thing is that this value of this phase seems to be completely generic. So there is nothing special about this phase. It looks like this phase looks consistent with assumption that phases in the standard model Lagrangian are completely random. Yeah, and what we measure in the CKM matrix, yeah, the phase seems to like completely ordinary order one phase, and it somehow gives us the confidence, yeah, that phases in the Lagrangian are something generic. Yeah, so there is no law, no physical law that forbids the phases in the Lagrangian. That there is nothing. So when you write some coupling in the Lagrangian, it should have in principle, it should have a random phase. That will be important in the following discussion. On the other hand, the theta parameter, or more precisely, there is a combination, as I was explaining, there is a combination of the theta parameter and the phase of the determinant of the quark matrix that is an observable here. This phase should lead to EDM of the neutron and some nuclei. And the effects of this phase have not been observed so far. And this is a big mystery why it's not. Yeah, so we think that the way we understand quantum field theory, this phase should be there. There is no reason why it shouldn't be there. The funny thing is that there's not even anthropic reasons, yeah, why this phase should not be there. So for the Higgs mass, people were often invoking anthropic arguments that we wouldn't exist if the Higgs mass were not like, we would perfectly exist if neutron had an electric dipole moment, yeah, with corresponding to theta further one. But so we don't know. I mean, for this we have some good ideas like axions, or there is some mechanism that is pumping out this phase from the Lagrangian. But yeah, so far we don't have the confirmation that this is the case. It's probably this theta parameter currently is the best argument for the existence of new degrees of freedom beyond the standard model. Or maybe the best argument in the particle physics sector, apart from dark matter in the universe. So,
may I ask a question there?
Yes, please.
You say there are no effects observed so far. The effect would be essentially an EDM of the mercury or of the neutron, or is there any other effect one could observe?
Yeah. So this is just this. Yeah. So
okay.
the EDMs of the neutron and some nuclei.
Thank you.
Okay, so we finished with d = 4. Yeah. So this everybody knows. Let's go to d = 5. Yeah. So we are we are looking at this Lagrangian and going to higher and higher terms in this expansion. And the next term after d equals 4 that we encounter here is d equals 5. And d equals 5 is very nice because, as I said, we have only there's very small number of operators that you can write. So basically, this is again called Weinberg operators, and they corresponds to this kind of contraction of the standard model fields LH LH. And then here we can put any of the 3 generation of the leptons. Yeah, so we have 3, 5, 6 possible terms like that. And now this coupling constants here, this Wilson coefficients can be complex. So this terms can violate CP. So when we put the vacuum expectation value of the Higgs, we get this kind of interaction. So with where the lowest, if you put the Higgs to 0, if you forget about the Higgs boson here, you're getting a Majorana mass terms, and this Majorana mass terms can be complex and off diagonal in general if we starting from a generic Lagrangian. So if we take the CP of that Lagrangian, again, remember, so I'm using here this 2-component notation. So so nu is a 2-component fermion, so and CP acting as nu interchanging it with nu bar. So if you take a CP, nu changes into nu bar and nu bar changes into nu. So the Lagrangian is not the same if this Wilson coefficients are complex. So this Majorana masses of neutrinos can violate CP. So now we don't usually in the quantum field theory we don't usually work with complex masses, not because it's forbidden, but it's because it's awkward to do calculations like that. So we always diagonalize masses. And so first we can do a unitary transformation which by a matrix U, which I foreshadow. Yeah, this is nothing but the PMNS matrix. And we can rotate the neutrino fields. And after the rotations, yeah, we choose, so after rotations, yeah, we're getting something that is rotated, but we can choose this matrix such that it's acting on this Wilson coefficients matrix of Wilson coefficient C. It diagonalizes the eigenvalues, the masses of so it diagonalizes this Wilson coefficient matrix C such that after action of this the PMNS matrix, we're getting something that is diagonal matrix. And in this new variables, yeah, this dimension 5 terms will be diagonal. So the neutrino masses are diagonal. But they can still be actually complex. Yeah, so this transformation by a PMNS matrix doesn't remove the phases from the eigenvalues. It still allows you to have the phases. So you have to do another transformation, which is just a phase redefinition of the neutrino fields so every neutrino field can be redefined by a independent phase, and we choose this phase such as to cancel the phase that is in this eigenvalue C. And after this rephasing, yeah, we got neutrino masses that are real and diagonal. So this is this is the operation that you have to do to get to the convenient form. And now something happened funny. So we started with something that is CP violating, but now there is no CP violation. Yeah, the neutrino masses are perfectly CP conserving. If you take the CP conjugate of this Lagrangian, you're getting the same. So CP violation is completely gone, but not so fast. So we removed the phase, yeah, in the neutrino mass matrix, but this is like a game of guacamole. The phase removed there, yeah, appears somewhere else. So somehow, when we constructed the standard model Lagrangian, we already somehow shoot our bullets with this phase redefinitions, and we use all this redefinition so as to make the standard model interactions to have the simplest form possible. And what we do in the standard model Lagrangian is we use all these phase redefinitions and rotations to make the interactions between the charged leptons, like electrons and muons and taus, and neutrinos to be flavor diagonal. So every lepton in the d equals 4 Lagrangian interacts only with its own neutrino. So electron interacts with electron neutrino, muon with muon neutrino, and so on. But now we had to destroy it, yeah, because now we wanted to get rid of diagonal and of phases in the neutrino mass matrix. So we did this phase redefinition, and we destroyed this wonderful picture. And now we have a mess here, yeah, because after we redefine the neutrino field, all the PMNS matrix and these new phases are appeared in this interaction. So of course, yeah, this is what gives you the effect of neutrino oscillations, yeah, which is very, very much analogous, yeah, to what happens in the quark sector, where you're getting the CKM matrix, yeah, in the charge carrying the interactions. So we have actually, but there is more, yeah. There's one more. There's more effects in the lepton sector than the quark sector. In the quark sector, we only have the CKM matrix, so we have this unitary 3x3 matrix with one phase. And PMNS matrix is an exact analog of the CKM matrix. It also has 3 mixing angles and 1 phase, and we call this phase the Dirac phase. However, in the neutrino or in the lepton sector case, we have one more effect, yeah, because we had to get rid of these phases from the Majorana neutrino masses. So we have also this matrix or these phases hidden in this vector P. So here we have 3 different phases, but we can actually show that overall phase is not relevant physically, so it will cancel out of all observables. So in reality, we have 2 phases there. I call them alpha and beta, and they are called in general Majorana phases. So now in the neutrino sector, once you allow dimension 5 operators into the game, the SMEFT predicts that there are 3 phases that will affect the phenomenology of a neutrino. So how do they affect how do these phases affect the phenomenology of a neutrino? So this the Dirac phase will affect the phenomenon of neutrino oscillations. So this is what happens in neutrino oscillations. Yeah, so we have some source that produces a neutrino, and we tag the flavor of this neutrino because we see what was the flavor of the lepton that was produced together with this neutrino. And then this neutrino travels in some macroscopic distance L, and it hits the target. And then we can again tag the flavor of that neutrino by measuring, yeah, what is the flavor of the associated of the lepton associated with the detection. So this is the process that describes neutrino oscillations. And one thing that is maybe worth mentioning here that has nothing to do with CP violation, but this is just quantum field theory process. Yeah, so there is usually when you explain neutrino oscillation, there is some gymnastic with quantum mechanics. Something propagates. You make assumption that the neutrinos are produced in some particular wave packets and so on. You don't need to do it. This is really a quantum field theory process that you can calculate with usual quantum field theory methods. You can calculate the amplitude of that, and you can treat neutrino as a propagating particle. And the only difference, yeah, is that you have this macroscopic distance here, yeah, it happens, yeah, that because of this propagation of some macroscopic distance, you can also have the phenomenon of the interference, yeah, between different mass eigenstates if the initial uncertain if the wave packet, yeah, that you started with, yeah, is and if the wave packet that you started with, yeah, has enough of quantum uncertainty. So all in all, yeah, you can just do this calculation, and in the same way as you calculate, I don't know, cross section, yeah, from the amplitude, and you find this. You can find this formula for the propagation, for the probability of oscillation of neutrino of flavor alpha into neutrino of flavor beta, and it's all just amplitudes. So these m's are just amplitudes for the production process or for the detection process that you calculate the usual way using Feynman diagrams. This d pi is the phase space for the production and the detection. And the only difference is that you're getting this factor of exponential factor, which contains the difference of neutrino masses squared. So this is all just quantum field theory in the usual way, with a tiny modification in the way you do the calculation. So I'm just showing you this formula because then it's very easy to see from this formula what is the how this process will be sensitive to the phases. So the production, so now the production of the neutrino will be governed by this Lagrangian, where we, after all this field redefinition of rotations, we have produced various phases. So we have the phases in the PMNS matrix, and we have this Majorana phases. So the production will be proportional. So in the production, neutrino is outgoing. So nu bar field corresponds to an outgoing neutrino. So you will pick up this phase factor. So you have U star and P star. And in the detection, the neutrino is incoming. So the neutrino field corresponds to a new incoming neutrino. And then this amplitude for the detection will pick up this phase factor U and P without a star. And then if you take the complex conjugates of that, so this is what you get. And then you're just putting these factors into the formula. And here upstairs, you see that you have production factors and detection factors organized in a particular way, and summed over all the mass eigenstates. So you're putting these factors, so you put U star U for the production, and you put U star for the detection, and lo and behold, this is the formula for the oscillation probability. If you also put this exponential factor from the neutrino oscillation. So this is this is like a very simple way you can derive the formula for the oscillation of probability of neutrinos. But what is interesting here is that because the way we were putting this various factors, the Majorana phases in this process have cancelled out. They are no more here in this formula because they were cancelling out between the production and detection. So the phase here and the phase they were cancelling out between production and detection, and they no longer appear in this formula. So they are not non-observable in this oscillation experiment. Okay, so now we have this formula for the probability of oscillation of neutrinos, and the probability of oscillation of antineutrinos is the same, but you just have to replace U and U star. So we have the same formula, and then we calculate the difference between these two, and then we're getting some after some calculation, we're getting this expression. So the difference, so the CP violating observable is the difference between the probability of neutrino with one flavor oscillating into neutrino with another flavor, with the probability of antineutrino of that flavor going into antineutrino of another flavor. So the difference between these two probabilities can be expressed by the parameters in the PMNS matrix, and then all these mixing angles appear in here. It's very much like a Yarskov invariant in the CKM case, and you also pick up the dependence on this Dirac phase. So the Dirac phase appears in this formula. If Dirac phase goes to 0 or to pi, then the CP violation is gone, and you also get dependence on the mass of all the three mass differences. So it is actually worth noticing that if you take the if you also use the same formula and you take alpha equals beta, then by CPT, nu alpha to nu alpha has to be the same as nu bar alpha to nu bar alpha. And this is indeed what's coming out. Yeah, you can easily show that these two this vanishes if alpha equals beta. So the formulas that we obtained here, yeah, they are there. So I'm showing this, yeah, so to illustrate a fact, yeah, that is kind of interesting, yeah, that CP violation is hard. So on the level of the Lagrangian, the CP violation looks something very generic, yeah. So if you're writing a term in the Lagrangian, you're putting a coupling constant, and it's you should assume a priori that this coupling constant can be complex, and if it's complex, there is CP violation. But now when we want to get to observables, there is like all these mounting problems. Yeah, so the neutrinos, you see that at least 3 neutrinos must exist in nature. Otherwise, if there is only 2 neutrinos, this CP violation will not be happening in the neutrino oscillations. All 3 mixing angles have to be non-trivial. Yeah, so I mean this is sort of the same thing. And 3 mass splittings have to be non-zero. And also the Dirac phase has to be different from 0 and pi. Yeah? So it's like with French administration. Yeah, so like, something looks very simple. Yeah, but there is all these conditions that you have to satisfy, and they are mounting, and yeah, you never know when it ends. And fortunately, it seems that all these conditions are satisfied in the neutrino sector. Yeah, so this is like the very recent paper by the T2K collaboration, yeah, which is an experiment in Japan, sending neutrinos and antineutrinos, yeah, from one place in Japan to another, and they showing, yeah, that the oscillation probability of nu mu to nu e and nu mu bar to nu e is different. And the difference, yeah, is consistent with the Dirac phase being close to minus pi half. Yeah, so this is the data. This is the expectation, yeah, of no CP violation, and you see that the data are very noisy yet with a lot of errors. Yeah, but they are giving some preference, yeah, for the large phase, yeah, of the maximal CP violating phase. So the best fit for this from this is minus 1.9 plus minus some 0.6-ish. And this is the same data for antineutrino, yeah, and they also, at least in these 2 beams, yeah, they go in the same direction. And so it seems that this phase is there. We will know quite soon, yeah, because there is many neutrino experiments that go after this phase, and we will know for sure in about 10 years when Dune experiment is up to speed, and this question will be solved. Yeah, I mean, unless this phase is very small, this phase will be measured with a pretty good precision. So you see that we can now interpret it, yeah, as another triumph of the SMEFT approach. Yeah, so the so neutrino masses, yeah, were already a big triumph, but at the time of the discovery, yeah, because the mindset was a bit different, yeah, it was not stressed that this is the case. But this is what we expect from the SMEFT, yeah, that we have this hierarchies, yeah, of different operators. We start with dimension 4, then we add dimension 5, then we add dimension 6, and that's what you first observe CP violation at dimension 4. That was in the 50s of the previous century. And then we observe CP violation at dimension 5, yeah, because that's the next place, yeah, where it should appear, yeah, and that indeed it seems that CP violation is something very generic, yeah, wherever it can appear, wherever phases in the Lagrangian can appear, yeah, they do appear. There is no law forbidding the phases in the Lagrangian, and we see they give you this physical effects, yeah, and they are they are being observed, and we almost have observed, yeah, the CP violation at dimension 5 in the SMEFT Lagrangian. One more. So one more thing, yeah. I was to discuss this thing, yeah. Why the CP violation is so hard, yeah. So this is the argument, yeah, that is given very often, yeah, in this discussion. So why the CP violation is something generic at the level of the Lagrangian, but it's so difficult to observe at the level of experimental observables. So consider that we have a CP violating amplitude. So A to B has this form, and then the CP, the amplitude for the CP conjugate process, A bar to B bar, has so-called weak phase. Yeah, so this has a CP violating phase here that changes sign if we consider a CP conjugate process. So now at the level of the amplitudes, we do have CP violation because these two amplitudes are not the same. But of course, at the level of observables, yeah, there is no CP violation, yeah, because we take the rate is m squared and this phase vanishes, and the rate it will be the same for both processes. So we have to do something better. So you know what we should do, yeah, because the CP violation requires a interference, yeah. So there has to be actually two contributions to the process with different phases and with different CP violating phases, and then we have a chance to see a CP violation in the rates. So let's take this assumption that we have two contributions to a CP to the process A to B, and again two contributions to the process CPA goes to CPB. And again, this is the weak phases, so they change sign when we go from process to the CP conjugate process. But now this is not enough. If you make this simple calculation and calculate the square of this amplitude and the CP conjugate amplitude, you find that they are exactly the same. So the existence of two interfering processes is not enough to actually ensure that the CP violation is observable, even though it's present at the level of the amplitude. So what you have to do is something more. You have to even complicate it even more and assume that there is these two processes which have this CP violating phases. But apart from that, these processes also have to have a CP conserving phases. So there is a phase of this amplitude that doesn't change the sign if you go to a CP conjugate process. And this kind of phases are often called strong phases, yeah, because, for example, they arise in strong dynamics, but not only. Yeah, there is several possible sources of this phase. For example, phases in loop amplitudes, when one of the particle or in the loop goes on shell, yeah, gives you a strong phase, or a width of a propagating particle, or more generally propagation of a particle gives you a strong phase. So there are the strong phases, but they have to be present together with the weak phases, and only then, if you when you now we calculate this rate of A to B and the rate of A bar to B bar. Now they are different. Now this cosine, yeah, is different. There is a relative sign between the weak phases, and the strong phases is changed. So if we have both weak phases, CP violating phases, the same as weak phases, and CP conserving phases, the same as strong phases, if we have both of them, now we can have a CP violation observable. If we take the difference of the two, you see that it will be proportional to difference of the strong phases between these two interfering processes and the difference of the weak phases between these two interfering processes. So this is why CP violation is so hard. Yeah, this is why there is so many conditions. So fortunately, neutrino oscillations are very lucky, yeah, that they can satisfy these conditions, because we have weak phases from the PMNS matrix, and we also have strong phases from the propagation of the neutrino in the coordinate space. So the strong phases is this E2 minus I delta m squared factor that appears in the neutrino oscillation formula. This is what provides a strong phase. This is something, this phase from propagation is the same for particles and for antiparticles, and this changes, yeah, this ensures, yeah, that all the conditions are satisfied. There's one more condition, yeah, that has to be satisfied, that I told you, that is related to the fact that the width particle and an antiparticle have to be the same. Or in the language of neutrino oscillation, this is the same as saying that the oscillations have to add up to the probabilities of oscillations have to add up to 1. So if there is a difference, if there is some, for example, a larger probability for electron neutrino to go to muon neutrino than for electron antineutrino to go to muon antineutrino, then because the probabilities have to add up to 1, then there has to be a compensating difference between the electron going to tau neutrino and the anti-electron going to tau antineutrino. So if this is some x, then this has to be minus x. So that's why at least 3 neutrinos have to be involved in the oscillations to see the propagations, because you have to satisfy these conditions, that the total probabilities sum up to 1. So this is why there is so many conditions that you have to satisfy to arrive at CP violation. Let me discuss very shortly one more thing, about neutrinos. So we have. I was discussing, that we almost discovered the Dirac phases in the dimension 5 Lagrangian. What about Majorana phases? There is 2 more CP violating phases. Are they? Can we observe them? Are they even physical? So the answer is no and yes to this question. So you can actually observe, in principle, the phases, the Majorana phases are physical, and they can be observed in another oscillation process, which are neutrino-antineutrino oscillations. So how you define what is neutrino-antineutrino oscillations? It's a little bit tricky, because we can say that neutrinos are their own particles. What is the difference between the neutrino and the antineutrino? You can define it in the following way. So for example, neutrino, when it hits the target, it produces the minus charged lepton, for example. On the other hand, if antineutrino, when it hits the target, it should produce a plus charge lepton. So this is the definition of what means neutrino and antineutrino. In reality, they are just two different helicities of the same particles. One is called neutrino and the other. So the left-handed helicity is called neutrino and the right-handed helicity is called antineutrino. So you can get the same formula for the oscillation rate, in the two, but there will be one difference. So as I was discussing, there is this. You can read how the phase enters into this formula. You can read it just from the Lagrangian. So the incoming neutrino, so in the production, neutrino is outgoing. So you have to use this nu bar, and you will pick up U star P star. And in the detection, antineutrino is now incoming. So again, you have to use the term with nu bar, and then you again have this U star P star. And now there will be no cancellation of the Majorana phases between this production and detection amplitudes, and you end up with the following formula, where you have a very similar formula like before, with 2 modifications. One is that this Majorana phases now appear in the final result because they don't cancel out, and the other is that you have this neutrino mass dependence in front, because in the process, when you calculate the amplitude in the process, you have to flip neutrino into antineutrino, which is the same as flipping the helicity of a neutrino, and flipping a helicity always costs you, for a relativistic particle, always costs you a price of putting a power of a mass into the amplitude. So you have mass squared in the rate. So now you see why the answer is that the Majorana phases are observable. Because if you calculate the rate for nu going to nu alpha going to nu bar beta and nu bar alpha going to nu beta, they will be different. The difference is given by this formula. Actually, the funny thing is that in this case, you don't even need 3 particles, 3 neutrinos to take part in the oscillation, even in the 2 oscillation limit. So I took a simplifying limit of this formula just so that it fits the page better. But you see that this this difference between the CP violating difference between the nu E going to nu bar mu and nu bar E going to nu mu is proportional to this Majorana phases. So they are observable. In principle, they can be measured in the experiment. Unfortunately, the rate is also of CP violation will be proportional to neutrino masses, which are very small. So this process is very, very, very suppressed. So there is little chance that in the near future we will observe it. Yeah, so this is a bit unfortunate. So there is two physical parameters in the dimension 5 Lagrangian that should be measured, but for the moment we don't have a good idea how. And yeah, so that calls, of course, for better idea, maybe both from the theorists and experimentalists. So there is some fundamental parameters we can go at that nobody has a good idea how to attack them. And with this advertisement, let me finish with dimension 5. Is there some questions at this moment, so that there is the moment of rest before the last part of this talk?
I don't see any questions on the chat, at least.
Okay, so let's go to dimension 6. Yeah, so we are in this Smith Lagrangian. Yeah, we already covered standard model. We already covered dimension 5. Now we go to dimension 6, and I was saying this is where all the hell breaks loose. Yeah, so we have literally thousands of different operators, and many of them, probably half of them at least, come with their own phases. So there is thousands of sources of CP violation. I will not be able to tell about all of it, so I will just make some selection, yeah, of the highlights. But let me give you some spotlight. So first, maybe something that is closer to your heart. So the dipole moments. So in this dimension 6 Lagrangian, you can see that some class of these operators of this dimension 6 are the dipole operators. So the dipole operators are defined that they have a field strength of one of the standard model gauge field. Then they will have two fermions with sigma mu nu in between them, and then they will also have a Higgs field. Yeah, so fermion is 3, 4, 6. Yeah, so this is the dimension 6 operator. Probably, as you know, yeah, these operators are very, very well constrained experimentally, and because especially for the lower generation. So let's just look at the electron EDM. Yeah, so if there is an experimental talk, yeah, there will be explanation. Yeah, what is electrons EDM? There will be some little balls with arrows and so on. I don't care. Yeah, I'm a theorist. Yeah, so for me, dipole is a specific term in the Lagrangian. So the dipole interaction, electric dipole moment of the electron is this interaction written in the two-component formalism, and it's the same as if you're looking at the Dirac formalism. Yeah, this is just gamma 5 in between this fermions. So this is a particular interaction term, yeah, and this is actually the correct normalization. Yeah, that this is exactly what you call electric dipole moment, this dE. So now in the Smith Lagrangian, we, for example, have this term. Yeah, this is the Wilson coefficient. This is the scale suppressing the operator, and this is the so it has the same similar structure, except for now we have instead of electron, we have a lepton doublet and we have a Higgs doublet that are married together. And instead of the photon field, we have a hypercharge field. So now if you break electroweak symmetry, you put the VEF of the Higgs, you change hypercharge into the photon. Yeah, you're getting this expression. Yeah, that you're getting cosine theta W from rotating hypercharge into a photon. You're getting a V from the Higgs VEF, and I forgot the square root of 2 here, of course. But if you don't forget the square root of 2, there is a square root of 2 here also from the Higgs VEF. And after that, yeah, you have a dictionary, yeah, between the electric dipole moment, yeah, and the imaginary part of this particular Wilson coefficient. So now, of course, there is a limit from Acme, which is this 10 to minus 29 e times centimeter. So this is some funny units, yeah, like something almost like astronomers, like using parsecs and ergs. But yeah, if I transform it to the units that I understand, this is the electric dipole moment has units of 1 over energy. So this is something like 10 to minus 16 over Jeff. So now I can translate, yeah, what I have this map between the Wilson coefficient and the experimental measurement. So if I so I can make the bound on the scale suppressing this dimension 6 operator, and the scale suppressing this dimension 6 operator is 10 to 9 GeV times square root of this imaginary part of this of the Wilson coefficient. So what does it mean? So it means something very, very exciting, yeah, because it's this now I just switch from GeV to TeV. So that's I mean more LHC mindset. So if this Wilson coefficient is of order 1, then that means that we probe the scales of new physics of the order of 10 to 6 TeV. So this is quite impressive. This is 5 orders of magnitude above what LHC can reach. And this means, yeah, that it's sort of halfway between the dimension, between the LHC and the probe of and what neutrino masses can probe. Neutrino masses can probe something like 10 to 12 TeV. So CP violation, the dipole operators in dimension 6, yeah, as you expect, because it's the next order in the effective theory expansion. So you don't expect better sensitivity, the sensitivity is worse. But it's still impressive. Yeah, we can go all the way down to up to the 10 to 6 TeV and probably new physics. So this is like the most optimistic assertion. There can be, but if you are in a more theoretical mood, yeah, this Wilson coefficients, if you generate it in some specific models, it never will be produced. It will never be never. Sorry, in most theoretical models, it will be produced with a suppression factor proportional to ME over V. The reason is that this operator, it violates a symmetry that is called chiral symmetry because it marries left and right. So it violates the same symmetry that is violated by the Yukawa interaction of the electron. So this is not a symmetry of the Lagrangian, but it's a sort of an approximate symmetry, yeah, that because electron mass is very small. So you would expect that new physics will also approximately satisfy, yeah, this symmetry. It will. The reason is that if it doesn't, then there will be loop corrections from the dipole to the electron mass, and then you will get some hierarchy problem now in the electron mass. So this is not a completely bulletproof argument, but in most models that or most elegant models that theorists write, that this dipole will be suppressed by ME over V. And if you take this into account, you have to put this ME over V into this formula. So you will get that you're only probing the scales to up to 10.3 TeV. But that's still impressive. That's 2 orders of magnitude above the LHC. One last thing is that actually there is yet another thing about this dipole interactions, that they usually appear at loop level. Yeah, so you need a loop factor, yeah, to generate this dipole. And if that means if you assume that your theory is weakly coupled, yeah, then this coupling here squared here that will appear here will be small, I mean order 1. So you will get 1 over 16 pi squared suppression, and then you only probe 100 TeV. So 100 TeV is still very very good. Yeah, so it's still order of magnitude above the LHC, and this is an important statement. It tells you that it's unlikely that there is new physics, or more precisely, new physics coupled with order 1 couplings, yeah, to the standard model up to 100 TeV. Why I'm giving this assertion? Yeah, because I was trying to to convince you, yeah, that the phases in the Lagrangian, yeah, are something generic, and this means that there is no reason why phases should be small, and the electric dipole moment of an electron, yeah, doesn't violate any symmetries of the standard model, or so it only violates this approximate chiral symmetry, and it violates CP, both of which are, I mean, the violation of the chiral symmetry is already taken into account in this ME over V factor, and the CP violation seems to be something completely generic. Phases in the Lagrangian seem to be completely generic. So if you accept this fact, it means that there is no new physics up to 100 TeV. And this is, we knew that before, yeah? So people who were hoping, yeah, for new physics at the LHC were always ignoring this fact. So for example, if you believe that there is like this 100 of SUSY particles, yeah, just behind the corner, you always had to believe in some sort of a conspiracy that this 100 particles will obey some completely different rules than what you are used to, and they will not produce any CP phases that you can observe in the electric, for example, as an electric dipole moment. Yeah, so it will be a huge. You would need a huge conspiracy, and in that case, yeah, it turned out that there is no conspiracy. Yeah, it just means that the fact that you didn't observe electric dipole moment, it means that there is no 100 particles at the TeV. Yeah, so this is an important, probably one of the most important guidelines, yeah, about physics beyond the standard model. Yeah, that either there is the biggest conspiracy since Roswell, or there is or new physics have to be above 100 TeV. Let me just give you one more thing about something that you like about the electric dipole moment of a neutron. The interesting thing about it is that it's a sort of it acts as a lightning rod. Yeah, so we will see this a little bit later, but maybe let me foreshadow it, yeah, a bit. So the point is that there is many operators in the Smith Lagrangian that will contribute to this observable. So if you calculate the electric dipole moment of a neutron from the Smith Lagrangian, then first you have a contribution at d equals 4, which is, this is a little bit of, this is quite of a shame, but we don't know what it is. Yeah, there is some coefficient that is of the order of the order of 1%, but we don't know exactly what it is, because our lattice methods are still so we can only estimate it. Yeah, that it should be. There's no reason it should be 0, but we don't know exactly what it is. But anyway, there is a sensitivity to dimension 4 operators, but at the dimension 6 operator, there's a sensitivity to a huge class of operators. For example, if you have a 4 quark operators in the dimension 6 Lagrangian with a phase, it will contribute to the electric dipole moments of a neutron. If you have a dipole operator, yeah, it will contribute. If you have a chromo electric operators, yeah, it will contribute. If you have this another Weinberg operator, yeah, G with 3 gluons and CP violation, it will also contribute. So you have this huge set of operators, yeah, that will be actually attracted, yeah, and will all go into the electric dipole moment of a neutron. And this is without taking into account randomization group running. Once you go from high scales to low scales, the operators mix with each other. And these operators that I showed here, they actually mixed into some other operators. And if there is a CP violation in yet some other sector, it will be transmitted by randomization group running into these operators. And again, it will show up as a sensitivity, yeah, in the neutron dipole moment. So neutron dipole moment is probably, if you calculate it, yeah, up to 2 loops, yeah, it will be sensitive to 100 different operators in the dimension 6 Smith Lagrangian. Yeah, so this is something impressive. Yeah, this is you're looking at one observable, but you're probing huge, very broad range of different possible physics at the high scale. Yeah, so that's the power, yeah, of this measurement. Now let me go maybe change gears and illustrate a little bit this fact about the relation between the high energy and low energy when we look at the CP violation in a completely different sector, which is the sector of the Higgs. So in the Higgs boson can also have CP violating interactions. And if you look at the dimension 6 operators, there is some class of operators that contain the Higgs boson and gauge bosons. And you see that there are these twiddles here. It means that this violates CP. So if we take this operator, I focus only on operators with electroweak gauge bosons. We have again Wilson coefficient. We have a scale suppressing the operator. We take these three different operators, and what they do is that they will affect the standard model interactions, between the Higgs boson and the gauge and the electroweak gauge boson. So in the standard model, Higgs interacts only on the tree level, only interacts with the W's and Z's in this way without derivatives. There is an interaction. Higgs always interacts in the standard model proportionally to the mass or mass squared of the particle. Now, if you add this dimensional 6 operator, you add additional interactions of the Higgs with a different Lorentz structure, and this will violate CP. So this effect will show up in various Higgs observables. For example, if you're looking at the Higgs decay into 2 photons, you will have the diagram that comes from the standard model, the loop diagram with the W. But on top of that, there will be this contributions from this contact interaction between the Higgs and 2 photons, which is denoted here with this coefficient C twiddle gamma gamma. And this will give you additional. So we could do a calculation, what is the width of the Higgs into gamma gamma, but there is no point doing it precisely for the sake of this argument. Enough to say that this standard model diagram is suppressed by one loop, and there is no one loop suppression here. So you will get a formula like that the width is modified with respect to the standard model by some order 1 number times 16 pi squared, because this doesn't have a loop, and then squared of this C gamma gamma coefficients. And you get a squared here because of CP violation. So you cannot have this is a CP conserving observable, so you cannot have a contribution here proportional to the 1 power of C twiddle. You always have 2 powers of C twiddle if you're looking at CP conserving observables. So what does it mean? So we just do a simple analysis. So we know the Higgs gamma gamma widths with a, let's say, precision of the order of 10%, which that means that we can put a constraint on this C twiddle gamma gamma coupling of the order of 3 × 10⁻². So give or take a cow. So this is like very, very approximate calculation. This is just to make a point, not to set real limits. Now, how does it translate to new physics? So this C gamma gamma comes from example, from this operator. So let's take, for example, this operator CHB twiddle. It will be, the relation between C gamma gamma twiddle and the CP violating Wilson coefficients in the D = 6 Lagrangian is simple. It's this times v squared over lambda squared. You're getting this v squared because there is a VEF of the Higgs that you need here. And that means that you take the if you take this limit on C twiddle gamma gamma, you get the limit on the scale of new physics to be of the order of 1.5 TeV times the square root of CHB twiddle. So that is very disappointing. That's we in the electric dipole moments business. We are used to the sensitivity to lambda of the order of 10 to 5 TeV. Here we're getting just order TeV. And this is even actually optimistic because, again, typically this CHB twiddle will arise at loop level, so there will be a loop level suppression. So you're really sensitive to physics at or below a TeV in these observables. So this is something that has to be kept in mind when you're doing the CP violation in the business, in the LHC. Also note that, yes, so if you see an effect in this observable, you cannot, because this is a CP conserving observable, you cannot tell that it comes from a CP violating operator. It comes from something else, some CP conserving contribution. So in the Higgs-2 gamma-gamma, it's very difficult to observe CP violation. So actually, it's not that, again, the CP violation is there at the amplitude level. So Higgs decays into either two positive or two negative helicity photons. And if you're adding CP violation, the relative phase between these two will be affected. Yeah, so you can, in principle, by measuring the polarization of the correlation of the polarizations of the two photons, you could tell whether the amplitude is CP conserving, or sorry, whether the amplitude is CP conserving or CP violating. However, this is very difficult in practice because we're dealing with very high energy photons and we don't have good polarimeters for high energy photons. Yeah, we can look at how they the plane of conversion of these photons into electrons in the detector, and there is some ideas that was there, but this is very difficult because when these photons convert, yeah, the electrons are so close to each other that it's very difficult to make any geometric analysis of what's going on there. Yeah, so this is difficult.
Adam, that's a really interesting point. Can I just interrupt you for a moment to ask a question about it?
Yes.
So there are experiments, for example, with positronium decay, where you get two correlated photons coming out, and you can use the polarization dependence of Compton scattering to analyze correlations in their polarization. Is that not feasible here?
No, because I mean the problem is that the photons from positronium, yeah, will have the MEV energies, yeah. So
yeah, sure. So it's really the energy scale that poses a problem here.
The problem is that the angle, yeah, of how how it. So the only way we know how to measure this polarization is by looking at the conversion of this photon into electrons. But these two electrons, yeah, that you get from conversion are so close to each other, yeah, that it's very difficult to see what is the plane of the conversion. Yeah, so also the LHC detectors were not built for that. Yeah, that was not the priority. Yeah, so maybe, yeah, I think it would be very interesting to think of, yeah, that maybe once people get bored, yeah, with the experiments at the LHC, to maybe do some more like fundamental physics experiments, yeah, with polarizations, yeah, that and how to actually change the detectors, what to install to make this kind of experiment. But for the moment, all experimental, even so there is some theoretical paper which I quoted here. When experimentals hear about it, yeah, they say no, it's not possible. It will be very interesting, but for the moment there is no data.
Okay, thanks.
But that doesn't mean that there is no possibility, yeah, to actually measure the CP violation the LHC. You just have to go to more complicated processes. Yeah, so the simplest process that I know that where you can see CP violation is a three-body decay. So Higgs can decay into photon and an off-shell photon or Z, and then this goes into two leptons. And you could have the CP violation, yeah, in this process, yeah, could come from this interaction, yeah, that I was talking about between the Higgs and the photon twiddle and so on. And you can see that all conditions, yeah, for CP violations are actually reunited in this diagram, yeah, because you have a weak phase due to this CP violating interaction. And more importantly, you also have a strong phase. The strong phase comes from the width of the Z. Z boson has a quite large width compared to other fundamental particles. Its width is of the order of 1% of its mass. Yeah, so this is something that you can use here. And then indeed, you can also, in this case, you can look at the polarization of the Z, yeah, by looking at how the Z decays into leptons, yeah. And the point is, yeah, that, yeah, this so now you're dealing, yeah, with the leptons well separated in the detector, and you can look at all the angles, yeah. So you have a good control of the angle. It's not a question of the conversion, yeah, of a photon, yeah, in the tracker, but you can really look at the for example, where the muons went and what is this decay angle. And if you measure the decay angle in the rest frame of a Z, then this decay angle actually tells you, what is the polarization of this intermediate particle. So if you're looking at if you take the differential width of this process, as a function of this decay angle of the lepton in the rest frame of the Z, it will have this structure, that it will have this 1 plus cosine squared theta and some CP even amplitude, and 1 plus cosine theta times the CP odd amplitude, and the CP odd amplitude will be proportional to gamma Z over mz, that this is the strong phase that you need to get CP violation. And then there is also this dependence on the weak phases. And if you want to detail, there is they are given in this paper. So in principle, you can look at this. You can search for CP violation. There's other processes where CP violation can be searched for example, Higgs to 4 leptons. Then you can look at the relative decay planes, of the two pairs of lepton. Also Higgs to tau tau and so on. However, this conclusion, that this that you can only be, even though you can look at the CP violating observables, there's conclusion that you're always sensitive to the C twiddle of the order of 1 or 0.1 at the best. So the conclusion that you're only probing the physics around the TV scale is still there. And then there is a question, so there is always, if you're looking at the CP violation, and you're getting some results, you always have to compare, to EDMs. Is a signal at the LHC compatible with the lack of observation of EDMs of electron or the neutron? And in this case, the answer is a very resounding no. And the reason is the following. So this is the operator. This is the operator corresponding to the electric dipole moment, and this is the operator that gives you CP violation at the LHC with the Higgs coupling to 2 photons. The problem is that you can go from this operator to this operator by closing a loop. So you have a Higgs gamma-gamma coupling that violates CP here, and then photon, of course, couples to electron, and Higgs also couples to electrons, at least in theory. So if you calculate these loop diagrams, so that you generate from this operator, you generate the EDM operator. And just by dimension analysis, you can you don't have to calculate this loop. So this loop has to be, there's a loop factor in the loop, of course. It has to be proportional to the CP violation in the Higgs sector, so that it has to pick up the C twiddle. It has to be proportional to the electron mass, because Higgs coupling to electron is proportional to electron mass, so it picks up the Yukawa coupling here. And just by dimensional analysis, D is 1 over energy, so it has to be ME over V squared. There is no other scales, that you can add here. Or instead of doing this dimensional analysis, you can look at the books and find the renormalization group running of the dipole operator as a function of this operator, and you're getting the same result. There will be also some log from that could be of the order of few from the normalization group running, but it will not change the conclusion. So at the end of the day, you'll find that this limit from ACME gives you the limit on this C twiddle gamma gamma of the order of 10 to minus 5. So that means that you are like 4 orders of magnitude below what can be observed at the LHC. And again, you have to invoke some huge conspiracies. For example, you can say, oh, but Higgs maybe not coupled to electron. It will, if it doesn't, there will be a 2-loop diagram, that again will give you bound a little bit weaker, but still strong. So it's very difficult to justify the existence of a CP violating physics in the LHC, given what we already know about the lack of CP violation in systems like electrons or neutron. So this is the conclusion. So does it mean that we shouldn't look for CP violation at the LHC? Of course we should, because this is we are measuring some fundamental coupling in the Smith Lagrangian. Every measurement is important, but you have to be realistic. That from the theoretical point of view, there is no indication, that you're supposed to find something. If you find something, you probably made a mistake, and either it's something else equally interesting, or it's an experimental error. So I see that my time is over. So I wanted to talk about yet one more topic, but there is no way I can actually abort it. So I wanted to talk also about the parameter, the measurements of CP violation, but I think that we'll have to wait for another day. So thank you, and let me stop here.
Thank you very much. Maybe we still have time for a short discussion. By one question, maybe. Yeah, I see one hand raised. Who is that? Skylar.
It's me, just in case no one else is jumping in. I'd be curious, Adam, to hear your thoughts on this sort of naive experimentalist approach where we take all of the Wilson coefficients that we have access to and forget a little bit about the running up to higher energy scales. But then when we have experimental results in different systems, we try to propagate it back down. So this is the inverse of the lightning rod problem that you showed us, and maybe it's a bit of a pessimistic way as well of looking at this advantage as a disadvantage when now you saw something and you want to know where it came from. So is maybe two parts of the question would be, do we find ourselves fundamentally limited in the end by calculations of matrix elements and so forth in particular systems? I mean, even for the neutron, we have the Weinberg operator and so forth with huge uncertainties. And then the other part is what happens if we get very unlucky and we see a signal in a way that we can't disentangle it from the low energy signatures that we see, and we can't access it by the LHC either to see directly what channel it came in. Then is there another theoretical tool at our disposal, or is this even a situation that we don't expect to occur?
So yeah, I don't have something very intelligent thoughts about it. Yeah, but one thing that one has to be aware. Yeah, if you see the signal, you will have a maximum limit, on the scale of new physics, and that will be super important for us. Yeah, because for example, now LHC thinks or CERN thinks about building 100 TeV collider, but will be 100 TeV collider enough? No, we don't know. So we need a beacon to know, where the new physics have to be, like some sort of a no-lose theorem, and this will be provided, by your signal. About the concrete implementation or complete model that explains your signal, you're right. Whatever the signal that you will get, there will be about 105 models. That will explain it equally well. And you can see, even like with stupid like xenon signal, you have 100 models that appear in the next day, and that you cannot avoid. This is the disadvantage of low energy experiments, that they are prone to many different interpretation. And this problem that you mentioned, that we have this huge hadronic uncertainties, that it will only make this worse, because we don't know exactly the relation between the high energy parameters and the low energy parameters. And I really consider it very shameful. I think it should be, this is something we should work much harder on, and we should get to the point, where there is we know this dependence, with at least like 10% accuracy. This would be, we don't need to know it with like minuscule accuracy. We don't need to know the precise relation between theta and the n, but we should know it with an error that is below 100%. And we should strive very hard, to get to this point, because one day we'll get a signal, and we have to be ready.
Okay, thanks. Pierre?
Yes, thanks again for the very nice talk again, the very nice lecture. I'm a bit frustrated that you didn't say anything about the capital D, of course. But,
there are slides, there is everything is on the slides, so and
very good. So at least we'll have the slides. Maybe we'll invite you to tell us about it later, In any case, so I was wondering, in fact, you say that apparently, this is a very good success of the SMEFT, that in fact phases are randomly distributed, and you can see them, and you can at dimension 4 and 5. What is your clue about the other parameters that you don't observe, this theta and the C gamma gamma you are speaking about? There is a fundamental reasons why they are not there, or there is no reason, and when it's to be.
Yeah, so there could be two reasons. Yeah, so one reason is that we misunderstand quantum field theory, that this theta is not a physical parameter after all. This is considered very unlikely, yeah, by most theorists, yeah, because we have some other evidence, yeah, that topological configuration, yeah, that do indeed contribute, but yeah, I don't know. So that I think that this possibility should still be kept in mind. And the other, yeah, that there is some mechanism, yeah, that is sucking out this phase, yeah, and we have a very beautiful mechanism theoretically that is called axion that explains, yeah, why the way this effect is not there. Yeah, so I think that axion searches are currently really one of the most motivated searches for new physics, yeah, just because the lack of the observation of the theta clashes, yeah, with this other piece of information that we got from fundamental physics, that phases are abundant, that CP violation is something generic, and nothing in the world forbids CP violation. Yeah, so that it's always if you write a Lagrangian, then it will be always there. Yeah, and there is nothing stopping you. So I think that this is really an important problem, and I think that it will be solved in my lifetime.
Okay, and about the C gamma gamma, even if it's more anecdotic, I suppose. So there is a good reason.
So I don't know what is the question about C gamma gamma. What's
well, it's the same. The coupling sounds to be very, very tiny, and there is a fundamental reason for that, or it was expected that it was very well constrained by an EDM. It's not a CP violating phase, but it's this parameter you are on with this slide. So sorry.
Yeah. So, but yeah. So this coupling doesn't exist in nature. Yeah. So this it just means that this is
okay.
a coupling. Yeah. No. So,
okay.
but there is
so it's very different than the theta.
Yeah. So this coupling comes from this. This is very different. Yeah. So this coupling comes from where okay. I'm lost. Yeah, it comes from this Lagrangian, and the lack of this coupling just means that the scale lambda is large. Yeah, if it's if it's
so it's as simple as that.
Hundreds of TeV, then there's no problem. Yeah, then it's suppressed. Yeah, by many orders of magnitude, and that explains why we don't see it. So yeah, so the lack of this coupling is
it's just a manifestation of the scale at which it should happen.
The new physics is heavy, and it's probably not just behind the curve.
Okay, thanks a lot.
Okay, last question, Stephanie.
Yes, thank you again. This was really super nice. I loved this lecture. Thank you. No, in fact, my question was the same as the one from Pierre. I just wanted to be sure that I got your point right, that so far we observe everything where it was supposed to be, CP violating, but theta. So I think you just covered that point. Thank you very much.
Yeah. So so far, what I was trying to say is that it seems that the Lagrangians that we write in the SMET approach, if we write them down, we should put all the couplings that are allowed by the symmetries with arbitrary phases, and this paradigm is consistent, yeah, with what we observe in the experiment. The theta is the one departure from this paradigm, and we don't understand why. And yeah, I hope that we will solve it one day. And the lack of phases, yeah, that coming from other operators is perfectly well understood, yeah, by saying that the lambda scale that's suppressing these operators, that means that the scale of new physics is very large, larger than at least 100 TeV.
Okay, thank you.
Okay, thank you very much, Adam. So we can close this session. Thank you again. I will clap.